Greetings. So, we will begin unit 2, which is really the formal introduction to the subject, and we will straight away get into the algebra of vector spaces and so on. So, we are really jumping into the framework of quantum mechanics today, and it is like how you probably learned swimming. As long as your parents told you that, okay, come on, get into the water, kuch nahi hoga, you keep staying out of it, and then once you are thrown in it, you pick it up in no time. And I hope you will enjoy the subject. It will help you in your career, and if nothing else, at least it will save you from getting fined by a cop if you are speeding, because you can always argue, invoke the uncertainty principle and get away with it. So, we will jump into the subject. Essentially, we are getting into the mathematical formulation of quantum mechanics, and mathematics is the medium. It is in fact more than a medium, perhaps. Galileo said that it is the language of mathematics, but perhaps there is more to it than just being the language of mathematics. It is an important tool, and what it does for us is allows our thoughts to be developed in a rigorous manner, such that these thoughts and the formalism that comes out of it will describe the laws of nature, and that is what we are interested as physicists. So, our interest in this means I really love the subject of physics for this reason, because it requires the rigor of mathematics, it requires the logical content of mathematics, the rigor of mathematics, and then it connects to the physical universe around you in a very beautiful manner. So, in my mind, I think it's wonderful to be a physicist. So, why and how it works this way is a mystery, and Wigner says that why mathematics is so appropriate to describe the laws of physics. It is a wonderful gift which we neither understand nor deserve, and I do not care if I deserve it or not. I love using it, and that is what we will do in this course. Okay? So, now we agreed in our discussion yesterday that of the state of a system, the mechanical state of a system, which we are used to describing by position and momentum, that will not work, because measurement of one disturbs the other and vice versa, and that whole system of Newtonian mechanics, Lagrangian mechanics, Hamiltonian mechanics cracks, it breaks down. And the alternative to that is that you need a mechanism to describe the state, mechanical state of a system, and we will agree that we will describe the state of a system by a vector, which is denoted in this notation which you see on the screen. This is a vector which we have not labeled as yet. We are asking what kind of labels must be put in it to describe the state of the system. Now, how it is going to connect to the properties, to the physical properties of the system, is something that will become clear as we develop the algebra further. So, we have to get into the algebra of the vectors. We will ask what do these vectors respond to, what are the operations that can be carried out on these vectors, and so on. And when we develop this algebra further, we will be able to connect it to observables that we carry out, observations that we carry out in a laboratory. In the laboratory, we do an experiment, we see the spectrum, we see a line of a particular frequency, it has a particular intensity, and those are the questions in which we are interested as physicists. So, we will get answers to all of these questions, but not tomorrow, not day after tomorrow, but as we develop the algebra further, and that is what a course in quantum mechanics is about. Okay? So, these vectors respond to operations. These operations are carried out by operators which operate on the operands. The vectors are the operands, and the result of this operation can be a new vector which is proportional to the old vector. The proportionality is this little a which is written outside that vector symbol, which is called as a ket. Okay? And what this equation represents is the result of an experiment. Okay? An eigenvalue equation in a certain sense expresses the result of an experiment. You carry out an experiment, you are carrying out a certain measurement, and measurements are represented by operators. So, you carry out the measurement on the system which is represented by the state vector. The result of the measurement may or may not be proportional to the old state vector. It may be. If it is, then it collapses, the system collapses into an eigenstate. Okay? That is what an eigenvalue equation is telling you, but this will become more clear as we discuss this further. Now, we want to get some information about the system. We have got some information about the system. What is the information we got? We got the result of the measurement which we have represented by the letter A. Okay? It could be the energy of the system, for example. It could be the angular momentum of the system. Okay? So, some measurement you have carried out, and then you ask, I have measured the energy, what else can I measure? You could have asked this question that, okay, I have measured the position, can I measure the momentum also? Yes, you can measure the momentum, but after that you come back and repeat the measurement for position, you will not get the same answer which you had got on the first time. Okay? So, repetition of measurement may or may not be consistent with earlier measurements. They will be consistent if the two measurements are compatible with each other, not otherwise. Okay? So, you carry out a measurement and you get a result, and now you ask what else can be measured, and suppose you find that there is some other property that you measure, and then a third property and so on, and you go ahead and measure as many properties as you can, and notice that we are using the language of the Hilbert space and the vectors and so on, but fundamentally we are talking about measurements. Quantum mechanics is about measurements. Okay? Quantum mechanics is very much about experimental physics. It is not correct to think of it as a subset of theoretical physics. It is very much, it has to do with experiments. Okay? The whole formalism of quantum mechanics is developed in terms of measurements. Okay? So, you are interested in knowing what all physical properties can be measured which are compatible with each other, and they will be represented in our formalism by operators, and if the measurements are compatible, then the corresponding operators commute with each other. So, it does not matter which operation is carried out first. So, if you can measure the angular momentum and the energy both, then you can measure the energy, after that you measure the angular momentum, and then you measure the energy again, you get the same result as you had got earlier. Okay? But if you measure something else which is not compatible, then they will not be commuting. So, that is the meaning of commuting, which is to do one operation, do another operation, and do them in the reverse order. Okay? Just the way you commute when you come here for the class from home, you come here, and then after the class you get back. You are undoing what you did. So, reversing the operations, that is commutation. And suppose you find that there is another property that you are able to measure, which is a property B. You are able to get the eigenvalue of B without disturbing the eigenvalue of A, and then you pick a second quantum number. So, the quantum number is the eigenvalue which is sticking there. That is the information you have been able to get about the system. And essentially, if these two measurements are compatible, the corresponding operators are commuting operators, then you can get additional measurements which you may represent by the letters A, B, C, D, whatever they are, and then you get a complete set of commuting operators. So, this is the terminology developed by Dirac which I am using, okay. And this whole formalism is in terms of vectors which were named by Neumann, by von Neumann, in honor of his guru David Hilbert. Okay. Hilbert was Neumann's teacher, and in honor of Hilbert, these are called as Hilbert state vectors. These vectors sort of reside in the Hilbert space, and this is a linear vector space, which means that you can add two vectors, you can multiply them by a scalar. That scalar is a complex number, and when you do that, it does not matter whether you write the scalar, the complex number, before the vector or after the vector, and regardless of that vector being scaled by a complex number, it is essentially the same physical state which is represented. The actual length of the vector is therefore not relevant, okay. And this is also the formalism which was strengthened by Dirac's work. So, the algebra involves a dual conjugate space. The vector space is defined along with its image space, and what you call as the real space and what you call as the image space is not relevant. One is the dual conjugate of the other. So, DC stands for the dual conjugate, and for every vector in the Hilbert space you have a dual conjugate space, and this vector space is spanned by a set of basis vectors. So, just like you have got any function which you can represent as a superposition of linearly independent functions, or in a 3-dimensional Euclidean space R3, you can write any vector as a linear superposition of 3 independent base vectors. Okay. You can write the vector A in the Hilbert space as a superposition of the base vectors, which are these EI, which are indicated in these ket vectors, and these are some complex numbers or scalars, and you are carrying out this linear superposition. So, it is essentially a linear vector space in which such linear superpositions can be carried out. And for this relation, there is a corresponding relation in the dual conjugate space. So, for every ket there is a dual conjugate ket. So, it is like twins in a certain sense, that they can almost replace each other more or less, yet they are different. One is in the direct space and the other is in the dual conjugate space. Okay. So, you have these dual conjugate vectors, and the algebra allows you to put them together like done over here. So, there is a vector here and it is a dual conjugate vector beta. So, for every alpha there is a dual conjugate vector alpha, okay. And if you take a different dual conjugate vector, then you can stack them together like this and define what is called as an inner product. And if you look at the notation, it looks like bra ket, and you slice the word and call the direct vectors as the ket and the dual conjugate vectors as the bra vectors. Okay. So, you have got a bra space and a ket space which are dual conjugates of each other. Then the significance of the term conjugate now becomes clear when you look at these properties that these vectors have, that if you look at this product, this is called as an inner product. If you look at this inner product and if you swap the labels, then you get the complex conjugate. So, the asterisk represents the complex conjugate, and obviously if the other vector, if the other label is the same as this, then you get a real number, okay, because a real number is also the complex conjugate of itself. So, the other property that you consider, there is no reason why you must consider this to be greater than or equal to 0. You could have thought of this to be less than or equal to 0 and then build the whole algebra like this. After all, the sign of what you call as positive and negative, it is arbitrary. You could have called the electron as a positive charge and the positron as a negative charge, and physics would not have been same. Number theory would have been same if you had called the positive numbers as negative numbers and negative numbers as positive numbers. Okay, arithmetic would have been the same. So, this notation is somewhat arbitrary, but here we have to make some convention and stick to it. So, the inner product alpha is either 0 or positive. Okay. You also define what is called as a null vector, which is different from the number 0. It is the inner product of the null vector with its dual conjugate, which is the number 0. Okay. The null vector itself is not 0, it is its inner product with its image vector, the dual conjugate vector, which is 0. And if this inner product, which we know, if you take a direct vector and its inner product with dual conjugate vector with the same label, then you know that it is a real number. Now, if this real number is given a value equal to 1, then you know that it is called as a normalized vector. And for an arbitrary vector, you can normalize it by dividing it by the square root of this inner product, because when you take the inner product of this with its dual conjugate, obviously you will find that it turns out to be equal to unity, right? The inner product will turn out to be unity. So, these are very simple properties which are important, and this what you get from the square root of this inner product is called as a norm, and we have denoted here by this double barred notation. So, the double barred notation is called as a norm of the vector. So, now if we take an arbitrary vector, we can write it as a superposition of some two vectors x1 and x2, and corresponding to this relation there is a dual conjugate relation in which you have the dual conjugate of v, which is written as a superposition of the dual conjugate of the elements in the superposition. Okay. So, over here, because this is in the conjugate space, you get the complex conjugates of alpha comes over here and the complex conjugate of alpha 2 comes over here. Okay. So, because of this complex conjugate property, if you swap the labels, I mentioned that you get the complex conjugation, which is in fact the reason that this is called as the dual conjugate space. You can define other combinations, okay, like you scale b by lambda, c by mu, add them up, then it is like having a net vector which is made up of lambda b and mu c. Okay. So, this is just a matter of notation, and I am deliberately using some of this so that you get used to the notation and learn to do the algebra with this. Okay. So, now if you have a vector like this lambda b plus mu c, which is your d, and you take its inner product on A with A. So, taking an inner product is, it has an analogy in our 3-dimensional Euclidean space. It is like taking the shadow of a vector along a certain direction. It is like the projection. It is like taking the scalar product. So, this is in fact often called as a, not just as an inner product, it is also called as a scalar product. That is the reason you find that name there on the screen. Okay. So, it is like taking the projection. So, what you have done is to take the projection of the superposition state lambda b plus mu c on the vector A, and you can get this lambda times inner product A b plus mu times A c. Essentially what you are doing is exploiting the linearity property. So, this is what is meant by working in a linear vector space. You can do it on the other side. You have a superposition in the adjoint space, and you do the same thing, but now the coefficients which are scaling come out with complex conjugation. Okay. So, what you have is the definition of the scalar product, also called as the inner product, and you also know what a norm is. So, it is giving you a measure of the distance. Okay. A norm is like a measure of length, it is a metric, it is giving you the size of that vector. Okay. So, this is your norm, it gives you the size of the vector. So, now we introduce a basis set. A basis set is one such that a linear superposition of these base vectors is capable of expressing an arbitrary vector in the Hilbert space, no matter what it is. It could be anything, any and every vector in the Hilbert space can be written as a linear superposition of this. There are two conditions which are automatically implicit in this. One, that the basis is complete, and second, that it is the base vectors are linearly independent. Okay. So, that is sort of implicit in this, and one has to keep track of this. This holds good in the direct space and also in the adjoint space, as you see. Okay. And this holds good for all the other vectors. So, I have expressed this for the vector A, and then also for another vector B. I can construct the adjoint of the vector A, okay, and then take the inner product of B with A, and now do this very simple linear algebraic property. And what I find that I can write this as a double sum I and j going to n, which is the dimensionality of the Hilbert space, and then you get ai star bj, and then you have got the inner product of ei with ej. Now, as you can do in any vector space, you can orthogonalize the linearly independent basis set. Okay. You can subsequently normalize it. This is something that you do using what is often called as the Gram-Schmidt orthogonalization, right. So, if these are the base vectors are orthogonal to each other and have unit magnitudes, then this inner product ei ej is nothing but the Kronecker delta, and you can contract this double sum over I and j using this Kronecker delta, and you are left with a single sum I equal to 1, I going from 1 through n, and you have ai star bi. What would happen if b is the same as a? You get ai star ai, which is the product of ai with its complex conjugate, which is a real number. So, it is the square of the modulus, and the sum of the squares will definitely be greater than or equal to 0. Okay. So, this is the inner product, which we now see that it will always be greater than 0, or it can also be equal to 0 if every component happens to be 0, then it will give you a 0. So, I will now introduce what is called as a Schwarzenegger inequality, and this is one of the important things that we will use to establish the Heisenberg principle of uncertainty. So, let me introduce what is the Schwarzenegger inequality. So, to do that, I first consider a combination of two vectors A and B, in which I have scaled B by a complex number lambda. Now, what is this complex number lambda? It can be absolutely anything that comes to your mind, which has got a real part and an imaginary part. You can think of any arbitrary complex number and scale the vector B by lambda, construct its dual conjugate. Notice that in the direct space it will be A minus lambda B, whereas in the dual conjugate it will be this bra A minus the complex conjugate of lambda times the conjugate of the vector B, right. But we do know that no matter what it is, the inner product must certainly be greater than or equal to 0. That is something that we have already seen. So, now you do it term by term, because you have got 2 terms over here and 2 terms over here. So, if you do it term by term linearly, you get 4 terms, 1, 2, 3, which is lambda star B A, and the last will be lambda star coming from here and lambda coming from here, and then you get the inner product of B with B. So, it is really very simple, and now you get this inequality. The sum of these 4 terms must be greater than or equal to 0. This is coming from the simple property that the inner product of a vector with itself is a positive quantity. So, we have this result. Now, this result holds good for every complex number, and therefore, it can hold good for some particular complex number which I like. Okay? I might like 2 plus 3i, or I might like 4 plus 6i, okay? Anything, because it holds good for every complex number. So, the complex number which I like is this. I choose lambda to be the ratio of the inner product of A with B divided by the inner product of B with B. I can choose it to be anything. So, I make this choice, and having made this choice, I substitute lambda in this equation by this choice. So, let us do that. So, this lambda is replaced by this choice, lambda star by the complex conjugate of this, the denominator is real anyway, right, and then this is lambda star lambda. So, it is the product of lambda with its conjugate. Okay. Now, what do you find? You find that this quantity in the denominator cancels this quantity in the numerator. Okay. So, you can just get rid of those, and then what you find is that these 2 terms, the third and the fourth term, are opposite to each other. They are the same terms, but with opposite signs, this one with a minus sign and this with a plus sign. So, they are the same terms. So, you have got a product of this complex number with this, and here this is written next and this one is written prior to that. The denominators are the same. So, the third and the fourth term are essentially the same, but with opposite signs. Okay. A complex number multiplying another complex number, that multiplication is commutative. So, it does not matter how you write them. Okay. So, what does it leave you with? It leaves you with the first term minus the second term to be greater than or equal to 0, okay? And you can multiply this term by the denominator over here, okay, both the terms. So, you get this inequality, and this inequality is called as the Schwarzenegger inequality. So, you just move one term to the other side. It does not matter how you write it with both the terms on one side or the other. Essentially, the result that you get is what is called as the Schwarzenegger inequality. So, we will now make use of the Schwarzenegger inequality here. Now, the Schwarzenegger inequality, this is the square of the norm, this is the square of the norm of B, right. So, the product of the squares of the norms of A and B is greater than or equal to, these 2 terms are complex conjugates of each other. So, it is the modulus square, right. And if this relation holds good for the square, you have a corresponding inequality for the square roots. So, the inequality that is written here for the square roots is essentially a direct consequence of the Schwarzenegger inequality. Now, we are dealing with some complex numbers. So, the inner product is some complex number z, which you can think of as being x plus I y, and for any complex number, its real part can be written, if x represents the real part, then what you know that the modulus of z, which is the square root of x square plus y square, is obviously greater than or equal to the real part of the complex number. Now, this is the result that we shall make use of, that the modulus of z is greater than or equal to the real part of this complex number, which is the inner product. Okay. So, now let us use this result. So, you have got the we consider the square of a plus b. we take the norm for the vector a plus b and take its square. So, you have a sum of a plus b in the joint space and a sum of a plus b in the ket space. So, you get 4 terms 1, 2, 3 and 4. The first and the fourth are the squares of a and b. So, these are the squares of the norms, and this is a complex number to which you are adding the complex conjugate. So, it is twice the real part, right. So, what does it mean? That if we now make use of this inequality, that the modulus of the complex number is greater than or equal to the real part of the complex number. Okay. So, we have got the real part of the complex number come in over here. So, the square of this a plus b will be less than or equal to, mind you, where the greater quantity is. So, here I have twice the modulus, okay, of the complex number. Here I had twice the real part. So, that is the reason I have got the inequality over here. So, now the rest of it is really very straightforward. So, I also now go ahead and use the Schwarzenegger inequality. What does it tell me? That AB is less than or equal to the product of these two norms. Okay. I have written it backward, the same inequality. Okay. Therefore, twice this modulus is less than or equal to twice of this, and it is twice this modulus which is coming over here. So, putting these two things together, I get the square of the norm of a plus b to be less than or equal to the square of the norm of a plus twice the product of the norms plus the square of the norm of b. Okay. Now, this is in fact called as a triangle inequality for a very simple reason, because it tells you something about how the sides of a triangle add up. Okay. So, if you have a triangle A and B, you will have exactly the same kind of inequality, right. So, this is called as a triangle inequality, and this holds good for vectors. In fact, there are these triangle inequalities which come into the picture also for operators, and at some point we will introduce these for quantum vector operators like the angular momentum operators and so on, where you have a different algebra involving the angular momentum vectors. But this is something which I will introduce a little bit later, in which once again you will meet triangle inequalities of this kind. So, in anticipation of that, I want to flash this result so that you sort of store it in your mind, and you will be reminded of this when we will discuss the angular momentum algebra later. Okay. So, the operators that we are now talking about are again linear operators. Okay. So, we now introduce the linear operators. So, we introduced linear vectors and now we introduce linear operators. What do these linear operators do? An operator would want to operate, and it needs an operand on which it would operate. And what would it do with that operand? It would carry out an operation, right. So, it is as simple as that, all right. So, you now introduce linear operators which will operate on the operand. So, here you have got an operator which operates on an operand, giving you a new vector, right, which may or may not be proportional to the old vector. Okay. And we have not put any labels over here in the vectors at this point, but we point out that the new vector may be proportional to the old vector, or it may not be proportional to the old vector. Is there any third possibility? I do not think so, right. It is either proportional or it is not proportional. It could be a completely different vector. So, either it is proportional as we see in the first equation here, okay, and the proportionality is this complex number A, or it is not proportional and you get a completely new vector which you cannot write as a product of a complex number times the old vector. So, these are the two possibilities that we consider. Okay. And the two possibilities are these. So, if it is proportional to the old vector, we have what we call as an eigenvalue equation, or else we have what is not an eigenvalue equation. Okay. So, there are two kinds of results that we get, either an eigenvalue equation or what is not an eigenvalue equation. And if you do get an eigenvalue equation, then the proportionality is what you use to label the state. Okay. So, the proportionality is alpha, and I now label the state as alpha. So, the labels are nothing but these proportionalities. These are actually the eigenvalues. Okay. So, the vectors are labeled by the eigenvalues of those operators of which the corresponding vectors are eigenstates or eigenvectors. And now we have already indulged in the terminology of what is an eigenvalue, what is an eigenket, and what is an eigenvalue equation. So, the properties of the linear vector operators are very simple, and this is the linearity which is indicated over here, that you can carry out operations by the sum of two operators, and it is the same as the result of the operation by one, to which you add the result of the operation by the other. Okay. You can scale up the operator by some complex number lambda, and the result is the same as scaling the result of the operation of A on X by lambda. Okay. And here is another property, that if you carry out two operations A and B, B first and A next. Okay. So, the product operator, what we are defining here is the meaning of a product operator. A product operator AB is one which can be factored into such operations. One part operates first, and then this gives you a new vector, and then on this new vector you carry out an operation by A, right. So, this is you also define what are called as null operators. So, a null operator would operate on an arbitrary vector, no matter what it is, the result will be the number 0, and the number 0 is not the same as the null operator. And then you also define what is called as a unit operator. What it will do to an arbitrary vector is to leave it alone. Okay? It will respect the original state and say that I am not going to disturb you. You also have operators. So, we have already defined product operators, and we introduced product operators such that the second operation will undo the result of the previous operation. Okay? I think married people can understand it very easily. Right? So, this is what the second operator does. Okay? It will undo whatever the first operator did, and this is called as the inverse, because the result is as if you have left it alone. Okay? So, it is as if you have operated by 1. Now, operators for which inverse exists are called as non-singular operators, because inverse is some sort of a division. It is like taking the number 10 and dividing by 10 to give you number 1, but division by 10 is possible, whereas division by 0 is not possible, right. So, you can run into some divergences and so on. So, to avoid that, some operators for whom inverse exists are the ones which are called as non-singular, otherwise they are called as singular operators. Now, if you have two operators x and y, and you do not know if they are equal to each other or they are not, then you can find out if they are equal to each other or not by operating on an arbitrary vector. If the result of these two operators on an arbitrary vector is the same, then the operators themselves must be the same. The condition is that the operand, which is the vector on which they operate, must be an arbitrary vector. If it is a special vector like the null vector, okay, or something like that, then it will not work. So, it has to be on the arbitrary vector. So, you can have the null operator which operates on an arbitrary vector and gives you the number 0. You talk about commutation of addition, because if you are adding two numbers, it does not matter if you write the addition as a plus b or b plus a. It is associative, which means that you can associate this b either on the right side or on the a side, on the left side. There is an association. So, here this is associated on the right, so that you get b plus c, whereas over here b is associated on the left, so you get a plus b. And addition is associative. So, a plus b first added to the result and the result added to c is the same as adding the result of b plus c to a, and it does not matter where you put this bracket, okay, that becomes irrelevant. So, you have this associative property, okay, and then you have an expression of the linearity. So, these are linear operators. So, the coefficients come out as scaling factors. Okay. Later on at some point we might also introduce antilinear operators, anti-unitary operators and so on, but I will leave it for the future. For the time being we will deal with linear operators. Okay. And we define these operations. The operators can operate on the direct vectors in the ket space or also on vectors in the adjoint space. On the adjoint vectors on the adjoint space, they operate from the right, and on vectors in the direct space they operate from the left. Okay. So, that is the direction in which they sort of operate. And you define for every relation in the direct space, there is a corresponding relation in the dual conjugate space. So, A alpha, the dual conjugate relation is represented by A dagger operating from the right on the adjoint of the vector alpha. What we have introduced here is a new operator which is called as the Hermitian adjoint of A. So, this is the definition of Hermitian adjoint of A. What it is doing is it is giving you the complex conjugate of the result of an operator A operating on the arbitrary ket alpha. Okay. So, for this there is a dual conjugate relation, and it is the dual conjugate relation which defines the Hermitian adjoint. Now, this multiplication of operators, when you carry out operations in succession, C first and B next and A last, okay, it is like taking the result of C first and B next, look at the resultant vector and then operate on that by A. You can do it, you can factorize this this operation as if you are taking the product of A and B and operate on the resulting vector which comes from the operation of C on the original operand. Okay. So, this multiplication is associative. Again, the meaning is the same, that the middle operator can be associated on the right or on the left. Okay. So, that is the association which is implied over here, and this is called as the associative property. And then operations may or may not commute. If AB is equal to BA, then we say that they commute, otherwise they do not commute. So, it is non-commutative. So, operations may or may not be commutative. So, we have defined here the Hermitian adjoint of the operator A. It is sometimes only called as the adjoint of A, and we ask this question that if you have two operations A and B which operate on alpha in this particular order, then we ask what is the dual conjugate of this vector. Okay. So, we follow the basic definitions once again, And the basic definition is this, that for this operation on alpha by B, the dual conjugate is defined as B dagger operating on this. Okay? So, this is the relationship between the dual conjugation. This is the just what we are using is the definition of the Hermitian conjugate, except that now we have to use it not for one operator, but for two operators A B. So, what will be the dual conjugate of A B? It is like A operating on this vector, the corresponding will be the A dagger operating on the adjoint vector, but the adjoint vector itself is the dual conjugate of B alpha. So, it will be alpha B dagger over here. Okay? All we have done, you do not have to remember these rules, you can get it from first principles from just the definition as we have introduced. Okay? So, what you automatically conclude is that the adjoint of a product is the product of the adjoints taken in the reverse order, because here you have A B, here you end up with B dagger A dagger. So, these properties come out automatically from the primary definitions. So, we define other products. So, this is an inner product that we defined. Now, we define what is called as an outer product. So, if the inner product was bracket, bra first and ket next, we define the outer product, which is the ket bra. So, this is an operator. The inner product is a complex number, it is a scalar. The outer product is an operator, because it can operate on a ket on the right and give you a ket, or it can operate on an adjoint vector bra on its left, and then it will give you a vector in the adjoint space in the bra space. Okay? So, this is an operator and it can operate either on the right or left, it can operate on a ket or on its right or on a bra on its left. Okay? But some kind of operations will be illegal. If you write ket first and this next with nothing after this, then it becomes an illegal operation. So, the notation has to be used with care. So, there are some legal products and some illegal products, okay? And you cannot get away with illegal operations in mathematics and physics, okay? And I hope not in life either. So, the direct, so we have defined the inner product and outer product, and we also define what is called as a direct product of vectors. So, you have got one vector J1 M1 and another vector J2 M2, okay, where J1 M1 and J2 M2 belong to different vector spaces. And if they belong to different vector spaces, a direct product of this kind is a legal operation. But if they belong to the same space, then it is not allowed. Okay? So, do not be too inspired by the first slide in which I showed you somebody getting away from the police by using quantum mechanics. You will not always be able to do that if you do something that is against the law. Okay? Only speeding you can get away with, but not this operation. Okay. So, you have got inner products, outer products, direct products. All of these are valid operations under certain conditions if you follow the rules. Okay? And you can associate this operation. So, look at this quantity over here. You have got a ket here alpha, an adjoint vector bra beta, and a ket gamma. So, you can associate this beta with this gamma first, get this scalar in this bracket, which is scaling this ket alpha, or you can also think of this as an operator alpha beta, which is an outer product. okay, the ket-bra outer product which is operating on gamma, and these two results will be exactly the same. So, this is the associative property of multiplication, but it applies only to legal multiplications, not otherwise. And this allows you to define the adjoint of the outer product as the adjoint of the ket-bra is the is this one. So, you have to swap the labels here. Okay. So, now we define a Hermitian operator as one which is self-adjoint. A Hermitian operator is one whose adjoint is equal to itself. That is the definition of a Hermitian operator. And what I propose to do now is a small theorem that the eigenvalues of a Hermitian operator must be real, and the eigenkets of the Hermitian operator belonging to different eigenvalues are orthogonal to each other. Now, this is a very important theorem. It has got consequences on measurements, because measurements, physical measurements, real measurements are represented by operators which are Hermitian operators. You do expect the result of a measurement to give you a real number. How long can you work with complex numbers? Okay, you can use complex numbers happily, because there is nothing imaginary about the complex number, because the imaginary part of a complex number is as real as the real part of the complex number. Okay? A plus IB, A and B are both real. So, there is nothing real, nothing imaginary about the complex number. What the complex number is doing is it is allowing you to do the algebra of two real numbers in one algebraic framework, which is the algebra of complex numbers. But when you carry out a measurement, the result of the measurement is going to pop out as a real number, and these measurements will be represented by operators which are self-adjoint, which are Hermitian operators. And that is the reason you have this important theorem that the eigenvalues of a Hermitian operator are real, and the eigenkets of the Hermitian operator belonging to different eigenvalues are orthogonal. So, they have no projection on each other. So, I will stop here today. I think there is time for questions. Compatibility in measurements is, first of all, it's a good question. Suppose a measure, if you take the hydrogen atom, you have got an electron and a proton. I measure the angular momentum of the electron. Okay? What the measurement does to the system is that the system collapses into an eigenstate. So, I get the value of the angular momentum of the electron. Okay? As long as I have not made this measurement, if I am asked what is the angular momentum of the electron, okay, my answer would be that it can be one of the any possible angular momenta, because the system will be in a state of superposition. If I carry out a measurement, I will get an answer. And what the measurement will do is the system will collapse into one of the eigenstates. I will get a result, and then I will say that, okay, this is the result I got. Now, after this, I come and measure what is the energy of the hydrogen atom. So, I will get it to be, I will get some answer which is some electron volts or joules or something in some energy units. Okay. And I go back and repeat my measurement of the angular momentum, and if I do not get the same result which I had got on my first attempt, I would say that the measurements are not compatible. Okay? If they are, then I would say that the measurements are compatible with each other. Think about it this way. Suppose you do not measure the energy of the hydrogen atom, but you say I want to measure the kinetic energy of the hydrogen atom. Okay, I am not interested in the total energy, I want to measure the kinetic energy of the hydrogen atom. You go ahead and measure it, nothing stops you, you will get some answer. Then you say that okay, I want to measure the potential energy of the hydrogen atom. Go ahead, measure it, you will get some answer. And then you ask, I want to measure the kinetic energy again. Okay. Can you do that for the mass of this water bottle? You measure the mass of this water bottle, you will get some answer. Now I ask you to measure the height of this water bottle, you will get some answer. Now I say, okay, please go and measure the mass once again. You expect the same answer as you got on the first attempt, right? These two measurements are compatible. Yes, but if in between, if you have measured something else, and that is what will happen if you measure the kinetic energy of the hydrogen atom, then you measure the potential energy and then you come back and measure the kinetic energy, you will not get the same answer as you had got earlier, because the kinetic energy and potential energy are not compatible with each other. The kinetic energy depends on the momentum, p square by 2m is the momentum, potential energy depends on the position, and these two are not compatible with each other. Okay. So, compatibility of measurements is a statement of which measurements or which set of measurements can be carried out regardless of the order in which they are carried out. Okay. Equivalently, these are represented by commuting operators. If you keep measuring just the kinetic energy and not interfere in between by a measurement of potential energy, you will get the same answer, because the system would have collapsed into an eigenstate of the momentum. Okay. And if it stays, if it has collapsed into an eigenstate of a certain measurement, it will stay in that eigenstate. Yeah. It will change only by a phase factor. The length of the vector itself is not going to change. Okay. So, a measurement induces the system to collapse into an eigenstate, it stays in that eigenstate, it continues to stay in that eigenstate if a compatible measurement is carried out, but if a non-compatible measurement is carried out, then it will not stay in an eigenstate, and therefore, any subsequent measurement will not yield the same result.
It's like acting force.
It is like
acting a force in the different direction in which object is moving.
in some sense, yes, but it is better not to use, not to invoke classical ideas of forces. Okay, because force is something we do away with. Okay. Force is something, it is a Newtonian idea. In fact, we do not use the idea of force even in classical mechanics when you get into Lagrangian mechanics or Hamiltonian mechanics. But I understand what you are saying. What you are saying is that you are disturbing it. Okay. No, it is because it is the square of the inner product, right, and the inner product of a vector with itself. How have we defined the inner product? If inner product of A with B is the complex conjugate of the inner product of B with A, okay. But if B and A are the same, swapping them will give you AA equal to the complex conjugate of AA with the A swapped, and they must be the same. So, what quantity is equal to itself? Which complex number is equal to itself? Only a real number is equal to itself. So, that is what makes it real. Okay. And the value of this real number, the sign that you attach to it is just a matter of defining how you define sign in number theory. Which hand is this? Right hand? This is my right hand. This is my right hand, right? This is my left hand. But if I was taught from the beginning that this is left and this is right, and if all of us went to the same school, we would have no problem, right? We would have no problem with the language. And the same with numbers. You draw a number line, put the number 0 here, plus 1 here, plus 2, plus 3, minus 1, minus 2, minus 3. But you and I went to a different school in which our teachers called this is plus 1, this is plus 2, this is plus 3, this is minus 1, this is minus 2, this is minus 3, and we all went to the same school, we would have no problem. All our arithmetic will turn out to be exactly correct. Okay? If you bring 2 apples and he brings 2 apples, we will have 4 apples, 4 real apples, and not 4 minus 4 apples. Okay? It's just a matter of, how you define these. Yes. The other is the dual conjugate space. So, you have got the direct space and the other space is the dual conjugate space. In some cases, the dual conjugate space may be the same as itself. The 3-dimensional Euclidean space in which we use these ordinary vectors, it is dual conjugate of itself. It is coming tomorrow. So, it can be the same in special cases, in general it is not. The example which I gave a little earlier, in fact, was essentially an example of a linear superposition, which is the measurement of energy of the hydrogen atom.
So, here measurement is eigenfunctions.
Measurement throws the superposition state into an eigenstate. So, the term which is used is the collapse of the superposition state.
So, here measurement is a kind of operator.
Measurement is represented by operators.
System,
yes.
And it is doing the
Exactly. Yeah. So, measurements are represented by operators. This is quantization. This in fact is quantization. Quantization means that you stop representing the state of a system by position and momentum, represented by state vectors, and represent physical quantities by operators. This is quantization. We are not defining it in terms of discrete energies and so on. In fact, discrete energies are not always the case. Many systems will have continuous energies. Actually, force is dispensed with even in classical mechanics. Okay, in the Lagrangian formulation, you don't use force at all. And force is not a great idea in quantum mechanics, because quantum mechanics, the question you have asked is about force, but the question about mechanics is not what force is. The question is, how do you represent the state of a system and how does it evolve with time? Right? That is our question, which we are trying to answer. The answer that we are going to get by the end of this unit is that the state of a system is represented by a vector in the Hilbert space. And how does it evolve with time? That will be given by the time derivative of this, okay, which is the del by del t of a ket vector. In fact, it will turn out that there are some other constants like IH cross and so on. So, IH cross del psi by del t gives you the rate at which psi changes with time. And what is this equal to? It is equal to the Hamiltonian operator operating on the state vector. and that the Hamiltonian operator is the sum of the kinetic energy operator and the potential energy operator. Force doesn't come anywhere in the picture. Okay, so you have answered the question. The question was, how does this, what is it that represents the state of the system? It is a wave function. How does it evolve with time? It is given by h cross del psi by del t equal to h psi, which is the Schrodinger equation.
We don't need any more.
And good that we don't need it. It will collapse to an eigenstate of the measurement, or eigenfunction of the corresponding operator. Measurements are represented by operators. So when you measure something, you will get some value, right? And you can get only one of the possible values that the system can have. So that is the eigenstate of the measurement.
Operator we are decomposing into eigenfunctions.
Huh?
That operator we are decomposing, means that we are expressing that as a weighted combination of eigenfunctions.
No. Operator is not written in terms of the eigenfunction. The result of the operation is a measurement. It is represented by an operator. The operator operates on the operand, which is the function. The result is a function which represents the state of the system. And this state will be an eigenstate of the measurement. It will be the result of the measurement. Okay? So don't get lost in the use of these words. Just think about it as a very simple process. Okay? It's not mathematics. It is not vector algebra. It's very simple common sense. You're talking about a measurement. You carry out a measurement. On what do you carry out the measurement? On the system. What represents the system? A wave function represents the system. Okay. So the wave function is the mathematical symbol for the system. It represents the system. It's like you being represented by your roll number or name or something. Okay. So that represents the system. You measure some property. So if we are talking across on the phone, I don't know what color t-shirt you are wearing, okay? And if anybody asks me what color shirt are you wearing, I would say that it is either white or pink or green or blue or orange or some other horrible color, right? But if I see you, I have carried out a measurement. If I have not seen you, it would be a superposition of all of these possibilities. If I see you, I carry out the measurement, and then I say you are wearing a shirt of such and such a color. So all those other 10 possibilities have collapsed into one possible, which is an eigenstate, because it is a possible color that you may be wearing, and that color does not belong to the X-ray region, right? So it has to be one of the possible states. It has to be one of the eigenstates.
These particle states should be finite or infinite?
It depends on the system. In some cases it is finite, in some cases it is infinite. If you ask what is the energy of the hydrogen atom, it can have infinite possibilities. If energy of the hydrogen atom, it can be anything. There are infinite possibilities. There are infinite possibilities.
But if we consider energy, so but what I read Yeah, of course, only if it is n equal to 1, n equal to 2, each have certain energy levels.
Okay, and then
So
n equal to?
N equal to 1, 2.
Yeah?
Like that.
Keep counting. Wait, I am listening.
Up to
Up to what? 10 billion? 20? Infinite. Right? Where do you stop? You don't stop. That is the infinite possibility.